All right, today we're cracking the code on artificial intelligence. We're going to take all that complicated technical jargon and translate it into simple, everyday ideas you can actually understand and use. Let's jump right in.
You know that feeling when you hear all these AI terms thrown around and you're just completely lost? Yeah, you are not alone. It really can feel like a secret language, but don't you worry, by the end of this, you are going to have that secret decoder ring. We're going to use some really simple analogies to make it all just click.
Okay, first up, let's build our foundation. We're going to start with the AI blueprint. We'll begin with the biggest, most general idea, and then drill all the way down to the nitty-gritty, the structure that actually does the thinking, kind of like a digital brain.
So at the very top of the pyramid, we've got artificial intelligence, or AI. The simplest way to think about it is just making computers smart, making them mimic how we think. Your GPS is a fantastic example. It's not just following a static map, right? It's analyzing live traffic, figuring out roadblocks, and making a very human-like decision to find you the absolute fastest route. That's AI in a nutshell.
Now, a massive part of AI is something called machine learning, or ML. This is where the computer isn't just following orders. It's actually learning from experience, from data. Think about Netflix. It sees you've watched 3 action movies starring the same actor, it spots that pattern, and it learns, hey, you'll probably like this 4th one. It's learning directly from what you do.
So let's go one level deeper. Now we're at deep learning. This is a much more powerful, more advanced type of machine learning that uses layers upon layers of digital neurons to find really complex patterns. Your phone's facial recognition, perfect example. One layer might identify the shape of your eyes, another a nose, and then a deeper layer recognizes how they're all arranged together to say, yep, that's definitely you.
And what are all those layers made of? Well, that brings us to the core structure, the neural network. It's a system literally designed to work like a human brain. Your bank's fraud detection system is a great way to think about it. It knows your normal spending habits, your usual neural pathways. So when a charge for a $2,000 speedboat suddenly pops up in another country, the network fires off a signal saying, whoa, hold on, that does not fit the pattern.
Okay, so now that we have the blueprint, let's look at the different kinds of AI minds. I want you to think of it like a toolbox. You wouldn't use a hammer to turn a screw, right? Well, in the same way, AI has all these different specialized models for all kinds of different jobs.
And the tool that everyone, and I mean everyone, is talking about right now is the Large Language Model, or LLM. This is the engine behind pretty much all the chatbots you see. It's been trained on a truly gigantic library of text from across the internet, so it's an expert in understanding and generating human language. You could ask it to write a professional, polite apology email for a delayed shipment, and boom, it knows exactly the right tone and words to use.
Now, this slide breaks down 2 other really important specialists. On the left, you've got convolutional neural networks, or CNNs. Just think of these as the eyes of AI. They are brilliant at seeing patterns in images, kind of like how a self-driving car can instantly identify a stop sign. And on the right, you have recurrent neural networks, or RNNs. They're the memory of AI. They understand sequences, which is exactly how your phone's autocomplete seems to magically predict the next word you're about to type.
So we have all these different AI minds, but how in the world do they get so smart? Well, it's basically like sending them to school. There's homework, there are tests, and there's a whole lot of correcting mistakes along the way.
Let's break down an AI study session. First, it gets its homework, but it doesn't try to cram everything at once. It just reviews a small batch of examples at a time. Second, it checks its answers using what's called a loss function, which is really just a score for how wrong it was. Third, and this is the key to learning, it corrects its mistakes using backpropagation. Think of an archer adjusting their aim after every shot. And finally, after it's gone through all the data once, it's completed an epoch, like reading the whole textbook one time before starting the cycle all over again.
But just like in school, there's a risk of studying the wrong way. In AI, this is a huge problem called overfitting. This happens when the model gets so good at the specific examples it was trained on that it basically just memorizes them. It can totally ace the practice test, but when it gets to the final exam, the real world, where the questions are just a little bit different, it fails completely. It never actually learned the underlying concept. Okay, so once the AI is trained and ready to go, how do we use it? This brings us to something really practical, giving the AI instructions. Because it turns out the quality of your results depends almost entirely on the quality of your questions. It really is all in how you ask.
Oh, I love this slide. The soup analogy just makes this so clear.
Imagine you go to a chef and give a zero-shot prompt like, make me a spicy soup. You could get anything, right? You gave no examples. But what about a few-shot prompt? You give it some context. I like tomato and miso soup. Make me a new one. Okay, now it has a much better idea of your taste. And the best of all is an engineered prompt. Here you get super specific. Make a spicy, low-sodium, vegan lentil soup. Now there's no guesswork. You're going to get exactly what you want.
Okay, for our last section, let's talk about one of the most critical topics out there, the guardrails for AI. How do we make sure that these incredibly powerful systems stay safe, stay helpful, and stay aligned with what we actually want them to do?
So one of the weirdest problems is something called hallucination. And it's exactly what it sounds like. It's when an AI just makes things up, and it says them with complete and total confidence. This quote is a perfect, if kind of funny example. The AI isn't trying to lie. It's just that its internal connections produced a fact that is completely, wildly wrong. And this is exactly why you always have to double-check an AI's work.
This leads us to the massive challenge of AI alignment. It's all about making sure the AI's goals match our goals. And the analogy here is just perfect. If you tell an AI to clean your PC, it might decide the most efficient way to do that is to delete every single file. I mean, technically it achieved the goal, but not at all in the way a human would have intended. Alignment is the incredibly important work of preventing exactly that problem.
And of course, there's bias. An AI is only as good as the data it learns from. So, if you train a hiring AI using a decade's worth of resumes from a company that primarily hired men, what's it going to learn? It's going to learn that being male is a key indicator of a good candidate, and it will then unfairly favor men, not because it's malicious, but because it's simply reflecting the bias that was already in its training data.
And that really leaves us with this final and I think critical question. We're getting incredibly good at teaching AI what to do, all the tasks, all the skills. But the real challenge that lies ahead of us is figuring out how to teach it what it should do. And that's something we'll all need to think about. Thanks for joining me for this one.